this guy is called an ACE matrix or a scattering matrix. And if you take up quantum field theory later, you will see this is something you will calculate all your life. Okay, we have studied reflection and transmission coefficients and ACE matrix in detail, and we'll actually work out a problem in the next video. Hi guys, so welcome back. It happens to be lecture 10 today, and we'll start something that is central to understanding physics. It was central to how people discovered subatomic particles like neutrons, like protons. So today we'll start discussing what's called scattering. If you ever take up experimental physics, this would be your bread and butter. Starting from the beginning of 20th century to even now at LHC, this is core physics. So maybe I'll spend a couple of lectures on scattering just to introduce you with the basic ideas. So historically, those of you who have who have had physics at an undergraduate level probably have already heard about it, right? So so let's discuss a bit of history, because really this is how physics progressed over the last century. And there's something called Rutherford scattering. I didn't know the exact date. Google tells me this was roughly more than 100 years back. So what is scattering? So what did Mr. Rutherford do? Well, back in those days, he didn't have access to too much technology. So what he did was something very nice, and that's the very heart of what scattering is. So he had basically something, and he wanted to, the short thing, the short answer is he wanted to study this object, and all he had access to are basically some radiation, nuclear radiation in this particular case, because these were helium atoms, doubly charged helium atoms, also called alpha particles. And he shown these guys on whatever he was studying. In his particular case, this used to be gold. And what he noticed was these guys scattered. So from their original path. So hence the name scattering. So they came in a parallel lines, and they were roughly scattered in this manner. Okay, great. Hence the name scattering. But going a bit deeper, what he noticed was actually that most of them didn't scatter. So imagine you have a big circle and a small circle, and what he noticed was something like this. Most of them didn't scatter. They went straight through, except one or a few scattered by quite a large angle. Maybe one of them among all of them. So what did genius that he was, what did he gauge from that? He gauged basically the picture that I drew. He gauged that an atom is mostly empty, which I think we all know by now, even from high school physics. It has a nuclear core and some revolving electrons, but it's mostly empty, right? And that's exactly what his scattering experiment told you, because all of them, most of them, went straight through, except a very few scattered via large angle. So this was how the experiment worked. It taught you that atoms are mostly empty. So this is why scattering is essentially, this is at the very heart of scattering experiments, right? It tells you it tells you the structure of this object that I drew here or that I marked here. And this goes on. I mean, this is the present story as well, like, because at the LHC, if you follow LHC physics, this is exactly what they do. Of course, now it's not a static target like that. They have basically collision, so they collide opposing rays, and they figure out the internal structure of matter. So that's the very heart of scattering. A few more. So, for example, a little later, something called the Compton scattering. You may have heard the phrase, the Compton wavelength. The same guy. I'll talk about Compton wavelength maybe on some other time. So this was apparently done, Google tells me this was done in 1923. And what was done is again the same structure. Some light was shown on an electron. And what Compton noticed was in the scattered, so this is called the incident beam, if because of obvious reasons, because this beam is incident, and this is called the scattered beam. And Compton saw that the frequency here, say omega incident, and the frequency here, say omega scattered, is such that omega incident is omega scattered. This was his observation. Okay. And if you recall, in our previous lecture, we have seen, for example, even for the harmonic oscillator. Do you recall the spectrum for the harmonic oscillator? The energy was given by it was given by n plus half h cross omega. So you see, energy is directly proportional to omega, which means the incident beam here, in this scattering experiment, the incident beam has more energy than the scattered beam, right? And this is what you would expect in physics, right? I mean, if you have some radiation falling on something, this material will absorb some radiation. This one will absorb some radiation. And the transmitted radiation, you expect it to have lower energy, right? So this is exactly what Mr. Compton saw here, Dr. Compton saw here. And he argued that the transmitted beam has less energy, and he also argued that basically these waves, because at that point of time these were thought of as waves, behave like actually particles, right? Why? Because you see the energy is lower, so it's almost like you are colliding between two particles. There are some collisions taking place between particles, and the emanating beam has lower energy. So it was one hint of what's known as wave particle duality, and this is one of the experiments that sort of hinted along those lines. There are a few more. For example, Chadwick did a similar experiment. Now he shown Ag2 plus, which is alpha particles, on a sheet of beryllium. This was beryllium. Again, same story. Most of them went through, except few knocked out protons. And what was left? I beg your pardon. Knocked out neutrons. So that led to the discovery of, if you know Chadwick, if you know his story, he got, I think, if I'm not mistaken, he got the Nobel Prize for discovering neutron, again via a scattering experiment. The idea is, again, not difficult to visualize, right? That you are shining light, and that is sort of knocking something out, because these lights have energy, right? Okay, good. Good. So the goal for today, with this bit of history, the goal for today is to try and formalize it. I will not go too much into details of it, but I'll start talking about trying to, organize these experiments in terms of maths. Okay, that would be the goal for today, using quantum mechanics. So quantum mechanics will try and come up with a theory that explains these experiments. That's what we do, right? We are theoretical physicists. Yeah. Okay. So scattering, right? So we'll let's look at the structure of what happened in each and every such experiments. Here and here. What was the structure of the problem? The structure of the problem is, let me know, you guys, if you agree, that you had a zero potential or a free particle, like a particle not acted on by any force. Then you had an intermediate region where there was a potential V non-zero. Imagine this is V0. This is V is equal to minus something. And then after a while, after a localized interaction, so this is what I mean by localized, that this is finite. This is what I mean by localized. This is quite important to realize, that this has to be a localized interaction. I'll go back to the picture before and tell you what I mean. You see, let me use this pen. You see, these were localized in this region, right? This was localized here, this was localized here, and these are what I had said V equal to 0. Here the particle, here the wave, etc., are not acted on by any force. Neither is it here, right? And there is something that happens in the middle. So this is the same model that I drew here. The waves were not acted on by any force here, neither here, but there was something in the middle which was localized, which was of finite length. So these basically form theoretical models. It's important to realize what we are doing. These are actually theoretical models of those experiments. These are theoretical models of those experiments. Okay? Good. If you followed my past few lectures, we have actually dealt with a few of these potentials. We have done a bit of work already. If you recall, for example, we had dealt with a step function. Oh, something like this, where your potential was 0, and potential was finite and non-zero. And we have seen how the waves behave, some waves, right? There were some wave functions that we had figured out here, and in the intermediate region, right? So this problem that I drew above is not entirely different from what we have been doing. So that's why we actually we have the wherewithals to actually deal with scattering problems already. Okay. So for simplicity, we have, as you see, we have chosen this potential. This is the simplest potential that you can find, that we can start with. this Vx is 0. Say if, how do I parameterize it? Let's see. How does Griffith parameterize it? Say if x is less than, say, minus a, is some minus v naught, and 0 if x lies between a and minus a, and if x is greater than a. This is this potential, right? Where I've just called this width as minus v naught, minus v naught. Okay. Now recall the Schrodinger equation. The Schrodinger equation was square plus psi double dot x, the time independent Schrodinger equation, I mean. This gave me v minus. Right? Do you recall this? Should I go back? Or maybe this is fine. This is fine if you recall this. Right. Let me check the sign though. I am always confused about the sign. Yes. Yes, the sign is correct. I always confuse the sign here. The sign here. So this is a Schrodinger equation that we have solved for a while. This is the same as minus h squared by 2m psi double prime x, and we know what this double prime etc. means, right? Plus vx is equal to e psi. So yeah, let's start with this one actually. So this was your kinetic energy, this was your potential energy V, this was your total energy T plus V, right? This was your Schrodinger equation that we want to solve. Well, this equation now becomes very simple because you have chosen your Vx to be 0 if x is less than equal to minus a here. So this term goes away. There is a psi. This term then drops out. So you are left with a very simple formula, which is minus h squared by 2m. Double derivative is equal to some constant times psi. Crucial that to note that this is a constant. This is x independent. X independent. For example, we have seen this already. In the simple harmonic oscillator, your En was, so this term is x independent, right? Good. This was for SHO, the simple harmonic oscillator. Great. So let me rub this. So this equation is actually very easy to solve, right? Why is that? Well, because this is a constant, you can write your equation as psi x is equal to kappa square k square times k squared times psi of x, right? Well, now this is in the outside region, and the solution of this, you already know what the solution of this is, right? The solution of this would be given by psi x. Can you tell me what the solution is? Or is it a minus? You see this, right? Because if I take a double derivative where k square, it depends on, basically the sign here depends on your definition. So let me define k square as 2me by h square. Yeah, these are all consistent. So you see easily that this is your solution for this equation. Why? Because if you double derivate it with respect to x, you pick up a ik whole square, which is basically minus k square. So you get this equation. Okay. Similarly, so this was region 1. Let me call this region 1, like from, by region 1, I mean this is region 1, where your v is 0. Let me call this region 2, and let me call this region 3. These are just names. Right. So what happens in region 3? Well, region 3 is exactly the same, because it's basically the same equation, right? Region 3 also has, in region 3, v is also 0 again. So you have the same equation, psi x double derivative should give you minus k square psi x. And of course, but now the constant will again be different. There is no reason for, however, the constant to be the same. So your solutions are, say, to the power ikx plus f minus ikx. The crucial point being, this e and f don't have to be the same as a and b, right? Let's go back to the experiment and see what I mean. I mean the energy here and the waves here don't have to have the same energy. In fact, they don't have the same energy. That's the whole point, because it has been scattered by this material. Except the similarity is the fact that this is a wave and so is this. So they are waves, but they are waves of with different parameters. Exactly, that's what we get here. So this was the incident beam. They are waves, but waves with different parameters, E and F. Right? Okay. Good. What happens in region 2? Well, region 2 is the is the most interesting. It depends on the choice of V, the potential V that you have here, right? It depends on the choice of V that you have here. So you have to tell me what this V is, and I could tell you what the wave function here would look like, right? Here I've chosen the simplest one, which is some negative constant. Yeah. But in scattering, try and think actually what the experimentalists are doing. They want to figure out something about this material which they don't know. Here in this case, this was beryllium. They wanted to study the atomic structure. Here again, this was gold, and they wanted to study the structure of these nucleons. Well, in those days, they wanted to study the structure of this atom, right? They didn't know about nucleons. So what is for the experimentalists, this V would actually be what they want to figure out, and what they would have access to are the waves in this region and in this region, right? That's what we wrote. We have a wave in the incident region and some waves in the transmitted region. So let's focus on these two. These are the things that the experimentalists would have access to. Good. Here comes the main point, that these wave functions, see, eventually these wave functions denote number of particles, right? The probability, rather, the integrated version gives you probabilities. So the point is that they are actually a linear, they are solutions of the same equation, right? They are solutions of the same equations. This one and this one. These are exactly the same equation with the same parameter, right? Which tells you that this solution is a linear combination of this solution. Is this clear? Because you are solving the same equation, right? So if someone finds a solution for you and someone else writes the solution in a different manner, they have to be linear combinations of the solution, because you cannot have different solutions for the same equation, right? Is this clear? You just have one equation. Which means your A and B here are combinations of E and F. So let me write an equation. Probably this will help. So your A is a linear combination. Okay, let me write actually in terms of the transmitted variables. Your B is a linear combination. Here I'm following Griffiths notation. And your F are a linear combination of the other two variables. You could have written as A equal to linear combination of F and G, and B equal to linear combination of F and G as well. It's the same thing, right? I mean, it's the same equation. Let me draw a picture that Griffiths also draws. It's very illuminating. So imagine this is the potential. Imagine this side onwards is region 3. Somewhere here is, oh no, I think I called it region 1, right? Sorry, not region 3, region 1. This is region 1. I think this I called region 2, from here to here. And this is your, again, region 3. So here I had some V, which I don't know what it is. This is precisely the point. I want some information about these potentials. But I know here the potential is 0. Here onwards the potential is 0. Likewise here onwards the potential is 0, right? Okay. So e to the power I kx, the solution that I wrote before, is basically a wave moving towards the right, and b e to the power minus I kx is a wave moving towards the left. Likewise, exactly here, I have called f e to the power I kx. Ooh, I have called f with a plus minus sign here. Sorry. Just trying to be consistent. I mean, it's, of course you can call it whatever. It's just I'm trying to be consistent with Griffiths. Yes, and a wave going in the towards the left hand side is E or minus I guess. So point being, if you have a minus here, it's a wave that moves in the opposite direction, or in other words, it goes x decreases as t increases, something like that. So imagine the wave was here, then it goes here, then it goes here, then it goes here. So x decreases as t increases if you have a minus here, and the opposite happens here. X also increases as t increases. So if you have a sign which is plus, these are waves moving in this direction, like here, like here. Okay, good, good, good. So now probably you understand why Griffiths call these to be the unknown variables, right? Because these this guy, the wave that escapes to infinity in the plus direction, and this guy, the wave that goes to minus, like far off minus x, are the unknown variables. Like they are the ones that the experimentalists have access to, right? Because these are the ones that gets collected in some machine. Someone is observing this wave and this wave, right? Not these, because these are the incident waves, right? These are the incident waves. Okay. Okay, so now, I mean, that's why he chose B and F here. No particular reason. Okay, as a matrix notation, one could write this as B and F is equal to S1, S2, S21, S22. I hope you know how to multiply matrices. Yeah, A and G, right? This is the same equation as here. Do you see that? These are the same equations. This one and this one are the same, exactly the same thing. For example, B is equal to S11 times A plus S12 times G, which is this one. And so on, and exactly the same for F, right? Good. So this one is called a scattering matrix or an S matrix. This guy is called an S matrix or a scattering matrix. And if you take up quantum field theory later, you will see this is something you will calculate all your life. Okay? You given incident beams like this, and given how they are measured by some observers at infinity, you will be asked to calculate this guy, because this is what you have access to. This is what you need to figure out, exactly as historically people have tried to figure out from here. You have access to this, you have access to this, and you want to know something about this in the middle. This is exactly what people have done for the last 120 years. So yeah, so nothing deep is happening, right? Okay, so this is called the ACE matrix, and I'll probably end with two definitions that we will take up today. So I'll define something called a reflection coefficient. Reflection coefficient and a transmission coefficient. They are exactly what the name means. They tell you how much of the wave is reflected and how much of the wave is transmitted. So you can tell me what reflection coefficient is, right? For example, from here, this is the amount of incident wave and this is being reflected back. So the reflection coefficient simply would be, say, R, let's call it R, so mod B square by mod A square, right? And of course, these are all modulars, because typically we have seen this before. These these A, B, uh, G, F, etc., they are all what I mean. They are all basically complex, right? Okay. Okay. I think I should call this G, right? This is called G here. Okay. So what would the transmission coefficient be? Likewise, the transmission coefficient will be calculated from this side picture. How much of it is being transmitted? So this guy is being transmitted, right? So it came and this guy is being transmitted. So the transmission coefficient would be T, let's call it T as again, mod F square by mod A square, right? Exactly as the names mean. You further demand something, which is that, since Griffiths is calling it G, let me call it G. You demand that this is 0. And this is very natural, right? You impinge something here and then it gets scattered and it then goes away to infinity, right? Nothing comes back, right? Nothing comes back. Because how will it come back? It just escapes to infinity, right? Exactly as you saw here. These all escape to infinity, right? Here and here. So in this direction, there is no wave, right? So you would naturally get, it's a natural expectation that your G is actually 0. There is no wave coming in this direction, right? So these are the coefficients such that G is set equal to 0 and G is set equal to 0. You understand the reason, right? And from this matrix, you see that these are immediately your S matrix elements, right? So your, for example, F square by A square would be, what would it be? S21, right? This is S21 square. Maybe S12. Let me check. No, S21, you're right. Again, mod square, because typically these are all complex numbers. This would be S11 square. So you see immediately if you know the scattering matrix here, you immediately can figure out the reflection coefficient and the transmission coefficient. Okay. Good. I think we can stop here. We have studied reflection and transmission coefficients and ACE matrix in detail, and we'll actually work out a problem in the next video such that you have some really good idea about what these coefficients look like and tie up with whatever we have learned in the last few weeks. Okay, have a nice weekend, and if you guys think this video was helpful, like, share, and subscribe to my channel, and see you in the next class.